Good evening, everyone. Welcome to the week 8 live interaction session. So, let's just wait for a few minutes for others to join before we begin our session for today. So, let's begin our session for today. Let me just share my screen. Is my presentation visible? Is my presentation visible? So I think there was a very bad internet connection today because of the rain that is happening here. So let's start our session for today. So welcome to the week 8 live interaction session for the course Polymers Concept Properties Uses and Sustainability. This course is offered by Professor Abhijit Deshpande sir from the Department of Chemical Engineering IIT Madras under the NPTEL program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering. I conduct live interaction session for this course for the July-November semester. So we have come so far as 7 weeks of this course, and we have discussed many things about the polymers, starting from its basics to its concepts to its properties, and we have also seen its uses and the sustainability perspective in almost every lecture as a small part. So in the last live interaction session, we've covered mostly on the viscoelastic properties of the polymers. We define the viscoelasticity or the viscoelastic response. What is a viscoelastic response, and how it is, or how polymers exhibit this viscoelastic response, which is something different compared to solids as well as liquids. After that, we discussed about the ways to quantify the contribution of the viscoelasticity, like what will be the percentage of the elastic nature or the viscous nature, which typically depends upon the time and the length scale as well as on the application. After that, we discussed about, again, even in the viscoelasticity, we discussed about how the response or the mechanical response will be in the glassy state and how it will change in case of the rubbery state, that is before TG and after TG. So after that, we discussed about the different effects, or like the, or what are the properties that usually as affect the viscoelastic behavior. I hope you can recollect. The first one was the temperature, and apart from that, we have the, I hope everybody is able to remember that one. So we discussed more about the temperature, how does the modulus gets affected by the temperature, and I also posed a question that what would happen for the modulus if we take it to a temperature less than Tg or greater than Tg. Apart from that, we discussed about, in continuation to the before lectures, we also discussed about the DSC as well as the TGA type of characterization technique, which typically explains or gives us an idea of how the properties of the material vary as a function of temperature. Then we went on towards the characterization of the viscoelasticity. Also, we call that as viscoelastic characterization. And then we over there tried to characterize the polymers using available set of techniques to understand their viscoelastic properties. So we discussed about the DMA, dynamic mechanical analysis, and how it helps us to, and how it does gives us an idea of the viscoelastic nature of the polymer depending upon the G and G dash value. So then we also discussed about the different types of dynamic tests, the creep test as well as the stress relaxation test, and then we also used the types of simple linear viscoelastic models to basically to model both the creep as well as the relaxation as well as the stress relaxation test. If you remember, we discussed about two types of model. One was the Kelvin-Weigert model, and then the other one was your Maxwell's models. So that is something what we discussed in the last session, the Weigert model and then the Maxwell model. And over there we use this model I mean, these models typically explains us or shows ho- the the viscoelastic nature of the system in terms of mathematical equations. So these are the two mathematical equations, and then to this equation we apply our constraints such as the constant stress or the constant strain, and then we try to determine their equations. Based on the equations that we obtain, we kind of predict whether this model will be suitable for this particular constraint, or whether the constraint is a is or whether the constraint fits the model, something like that. So like that we discussed for both the Weigett model and the Maxwell's model, where we determine that if a constant strain is applied, or you can say stress relaxation, then the Weigett model is a poor prediction. And in case of the Maxwell model, we saw that if a constant stress is applied, or you can say a creep, then in case of those, the Maxwell model does not predict the viscoelastic properties of the material. So this was what was discussed till the last session. So in today's live interaction session, we do discuss about the viscoelastic response of the polymer, but then here we come with a different perspective. So if you see, the week 8 live interaction session has totally around 8 different lectures. So today we will have more of a discussion towards understanding the testing of the polymers, or you can say the commercial the trade test in the polymers, then the properties of the blends. So we discussed the blend somewhere in the week 5 or 6 live in week 6 of the course. So we try to um, add more understanding towards the properties of the blend. Then we discuss something about the biomimetic properties of the polymer and try to understand about that. And then we conclude that with the diffusion of polymers. So trade test of the polymers is something very similar to what is something very specific towards the application of the material, or you can say of the polymer. This is something that basically determines whether the particular product that we get, or whether the particular product that we fabricate is suitable for the commercial application. Typically speaking, it determines whether, or it's a kind of a quality testing to check whether the product is good for a commercial purpose. To check the commercial feasibility of a particular product, we do this trade test. So these trade tests do not determine the property of the materials that we are using to prepare them, whereas it tests the property of the product that we tend to use it for our application. So this more is of more importance in these kind of trade tests is given to the final product, rather than to the polymers that rather than to the materials that is used to make the final product. So over here it can be polymers. So different types of trade tests do exist, and each one of them basically helps us in determining different types of properties of the object, or whether they are suitable for a particular application. So speaking of the mechanical perspective, the common trait tests that are used to determine the commercial properties, or you can say the commercial nature of the product. So we have trait tests such as hardness test, scratch test, puncture resistance, and tear strength. So these are the different types of tests, and depending upon what kind of the application it is, or how the product is, we use different types of these mechanical tests to evaluate the property of the product that we have in hand for that particular application. So let me just write that down. First we have the hardness. Next we have is the scratch. After that we have puncture, and after that we have the tear. So the tear strength is typically something more applicable to the material which is in the form of sheet. And so that's why I said each and every type of test basically comes in with a certain constraint to it, to where it should be applied. So this trade test usually depends upon the application and where it is used for the testing. So to determine the hardness, as we have mentioned, the first property to evaluate is the hardness. So this hardness is usually, the hardness of the product is usually evaluated by a test so called as nano indentation. So what typically this nano indentation process is that you have a load which is in the form of like which has a tip or a point of contact, and which has a tip. So this load is basically placed on top of the material that you want to actually test. Then this load is pushed, or you can say is indented on top of this material. Depending upon the load as well as the material property, there will be a displacement in the tip of the material. That particular displacement, or how much the tip has actually moved inside the material, is usually calculated, and based on this the hardness of the material is usually evaluated. So this is a kind of an indentation test that is used, or you can say this it's like a commercial indentation test that is used to evaluate the hardness of the particular product that we have in hand. So the major advantage of this indentation technique, or the way of determining the hardness, is that it is a quick test, it is quick in nature, and it is easy, and moreover it is inexpensive, as well as that the test can be performed in any part of the material. So this is typically the advantages, or you can say that these need to be, or you can the trade tests usually have these kind of advantages within them to evaluate the properties of the product for the particular application, so that it is not more it is better, it is typically we do this test to determine the quality. So if the process is in itself is not very easy, or it's very expensive, then it actually fails as a commercial item, so a commercial material. So the tests that are usually developed for understanding the properties of the products are usually need to be quick, and then they need to be easy to be done, as well as they should be inexpensive, so that multiple products can be tested for their quality, or multiple materials can be tested for their quality for a particular application. So several types of testers are actually possible. In case of polymers, we typically go with Shore A, Shore D, and Rockwell test. But apart from that, there are also tests that are tests other types of tests that are available towards evaluating the hardness of the material, such as the Nuke test, Brinell, and Vickers. So these are also the types of tests that are available to determine the hardness of the material. So this is typically for, as we have discussed here, these are for mechanical. But again, we have multiple applications where we require new materials to be developed. So in order for that, we need to also evaluate the other properties of the product, such as optical properties, electrical properties, and thermal properties, tribological functions, like how much there will the friction be if you keep a particular material, or how well this can act as a lubricant for you can say, if there is a higher friction, then, and if we need to use a lubricant, then how far this particular product can be used as a lubricant. So we need to understand the tribological properties of that particular material, or we need to, or if you want to see the degradation properties, then we need to check that, or if you want to see the optical properties, electrical properties, then some sort of packaging applications. So polymers are typically used for multiple food packaging applications as well. So we need to see whether these food packaging degrades, um, how it degrades, whether does it degrade within a short period of time, or it stays for a very long time, that it also pollutes the environment. So for depending upon the type of application, that tests will vary, and depending upon the type of product also, the tests will vary. So in order for the to determine the electrical properties, or you can say the electrical to determine the electrical conductivity or the electrical properties of a particular product, we go for something so called as the surface resistivity. So this, initially we discussed about the mechanical properties or mechanical trait test. Now we go for the electrical properties or the electrical trait tests that are used to evaluate the electrical properties of the material, or you can say of the product that we want to design. So surface resistivity is one such property that we have to evaluate to determine the the aptness of a product for electrical application. So how is surface resistivity different from the normal resistivity that we use, or that we already know? Is that resistivity, what we actually know, is actually a property of the material, and that is of volume resistivity. So typically resistivity, whatever we discussed, is nothing but is the volume resistivity, and it is a property of the polymer, of the material that we are taking under consideration. However, surface resistivity, it is typically more of the, it is the resistivity which is more often that we have, that we described here, is about the particles on the surface. So since we discussed only about the resistivity along the surface, here this resistivity will be affected by the environmental conditions as well. So you can write it here that this depends upon the particles in the surface. So if there is any dust accumulation, or if there are any impurities that are present on the surface of the particular product, then the resistivity will change accordingly. So that is the reason this is surface resistivity is not a material property, but it's a property of the, but it's a property that we usually test or do, or that we usually want to know to determine whether this particular, whether that particular product made out of this material are suitable for a particular application. So if you want to relate surface resistivity and volume resistivity, then that is usually given by a formula. So surface resistivity is nothing but it is volume resistivity by the thickness of the thin film. So usually in order to determine the volume resistivity, we usually go for a standard 4 probe or a 2 probe techniques, wherein we try to evaluate the conductivity of the or the resistivity of the material based on the IV curve, and you by calculating the volume resistivity and then the thickness of the film that we are going to use, we can calculate the surface resistivity of the particular system. So again, so these status are typically for determining the commercial feasibility of a product that is prepared by the material, and this does not evaluate the or these properties do not depend upon the properties of the material, or they are not does not depend upon the properties of the material. So this is about a very quick or you can say a very small description about the trade test. Now we from so after this we move on towards the polymer blends. So we have, so in the course we have discussed about the polymer blends before. So this section also will be something more of an addition to what we have seen previously. So polymer blend as such, it means that you are mixing two polymers. So you take polymer 1 and polymer 2 and you basically blend them, you basically mix them. Polymer blends are not same as copolymers, because in case of copolymers, what actually happens is the monomers are usually, or you can say, if homopolymers are typically connected through a covalent bond, but in case of a polymer blend, it is a mixing, or you can say a molecular mixing between the two polymers. So again, since you are going to mix two polymers, there can be a chance that the blend that you obtain finally can be a miscible blend or immiscible blend. So depending upon whether the blend is miscible or immiscible, the properties of the blend will vary, and it will vary significantly. So what could be typically the reason why we want to actually make polymer blends? Or when do we actually think about making a polymer blend? Anyone? Yes, any idea on why we make I mean, we actually want to go for making a polymer blend? So that is typically to improve upon the properties. So depending upon the property of our interest, we actually want to improve upon the depending upon the property of our interest. In case of a particular polymer do not exhibit, or let's say for example, if you want to have two properties incorporated into a particular system, or if you want two properties together in a particular system, and for example, if there are no such polymers which can have, or if there are no such materials or polymers which can have both these properties high enough, then we typically think about polymer blends. So in case for example, let's say we want to, again the same example of what was discussed in the course where we talk about polyaniline and polyvinyl alcohol or EVA. So in those cases, the problem with the polyaniline was that it cannot actually form film, as well as the processability is difficult in case of polyaniline. But whereas if you see in case of polyvinyl alcohol, they can form film as well as they can be easily processed. However, compared to polyaniline, the electrical conductivity of polyvinyl alcohol is very low. It's typically an insulating polymer. So by making a blend of polyaniline and polyvinyl alcohol, we can make the polymer, we can make the system to be easily processable. The film forming ability will improve. At the same time, the electrical conductivity, depending upon the fractions of the polymer, can also be enhanced. So typically, to improve upon the properties or the two contrasting properties in both the polymers, we go for something called as polymer blend. So as we were discussing that there can be two chances, one is a miscible and another one is immiscible. So depending upon the type of polymer blends that we obtain, the properties of the polymer will vary significantly. So if you are going to go with miscible polymers, the value of Tg is going to change or is going to be different compared to if in case the polymers form immiscible blends. So how does the Tg will vary if we go for miscible blends? So in case of miscible blends, since there is a good polymer mixing, there is a intermolecular mixing of both the polymers, the glass transition temperature that we obtain either through differential scanning calorimetry or the dynamic mechanical analysis, we can obtain that the Tg will be a single point. So it will be like a combination of two. So it will be a single Tg, and this particular Tg will lie between the Tg of the two polymers. However, in case of the immiscible blend, that is not the case. Over there, you can observe two Tgs. So, depending upon the type of blends that we obtain, the value of the glass transition temperature will vary accordingly. Now, what we are more interested or what we need to understand more is which one is better, or you can say if we have two homopolymers and then whether mixing or whether blending them will be suitable or forming a copolymer out of them will be suitable, or we can put it in this way, whether which one will be more suitable or more ideal, or how the properties will vary if we go with the mixing of two polymers or if we go with forming a covalent bond between both the polymers. So again, this is a more straightforward answer, and you can say that this is completely obvious that the properties will be contrastingly different. It will be strikingly different when you form blends out of homopolymer and when you form copolymers out of the homopolymer systems. So if you take the example of what was discussed in the course, that is your ethylene propylene, when they form blend, when the polyethylene and polypropylene polymers, if they form blend, here the properties that we wanted to see how it will vary is the impact strength. So if we form polymer blends out of ethylene and propylene, since both these polymers typically have similar impact strength, the impact strength of the polymer blend that we obtain will almost be same. However, when both these ethylene and propylene they form copolymers, there will be a significant variation in the there was a significant variation in the impact strength. So based on the combination of these two polymers, either it can be like an additive, that is just the addition of both these properties, or it can be a synergetic increase in the property, or it can also be a condition wherein there is a depreciation in the overall properties of the material that you obtain. So typically what we want is either it should be additive of both, or that should be a synergetic increase, that is the benefits should typically help in increasing the property greater than what the individual polymers exhibit. And this is what is typically desired, because nobody actually want to make a system wherein the properties is going to be lesser compared to what you had for both the polymers that you take for preparing them. So here in case of ethylene propylene, if you see the impact strength when you form a copolymer out of them, there is a synergetic increase or a relatively a larger increase in the impact strength compared to either ethylene or propylene. So this typically is basically because of the variation in the domain which impacts the materials. So the covalent bond that is formed between these monomers typically affect their properties or affect their final properties. That is what we discussed even in the polyaniline and polyvinyl alcohol system. So if you see that polyaniline, it has certain advantages and certain disadvantages that goes well with the polyvinyl alcohol as well as such. By making a blend out of these two polymers, we try to combine their respective advantages so that we can get a system which has much superior properties compared to their individual counterparts. So here it is about the film forming ability, bringing about the film forming ability, processability and electrical conductivity in the final blend system. So what typically happens is when we start adding polyaniline to the polyvinyl alcohol, we observe that there is an increase in the electrical conductivity. This typically happens after a certain volume fraction, and the major reason why this happens is because of the fact that these polyaniline, which are dispersed throughout the matrix, starts to interconnect with each other and form a domain. You can also say that they start to percolate and form networks, interconnected networks of polyaniline in polyvinyl alcohol matrix, and that interconnected network structure improves the electrical conductivity of the overall polymer blend that we take. Again, it all depends upon what kind of application we are targeting and the individual polymers that we have in hand. Some cases the formation of copolymers will be beneficial, just like how you observed in case of ethylene and propylene. In other cases, it is better to go with, in other cases, the polymer blends might exhibit better properties compared to what you observed in cases of the copolymers. So just a second. Let me share my screen once again. So let's okay. So this was typical, this was something that we had to discuss for the polymer blends. Now we move on towards the biomimetic polymers. Biomimetic polymers is, that concept is very easy to understand. It basically means that you're going to mimic the natural organism and their mechanisms that they typically exhibit. So if you see, for example, you can take for example some sort of artificial sensor or artificial skin that people actually develop these days. So the major thought process behind, or you can say the fundamental thought process behind these development, is that they should try to make systems in such a way that they impart functions into the system so that they exhibit properties or exhibit functions similar to that of the natural skin. So you try to make something artificial by, or you try to make something so that it actually mimics the nature. So that is the typical concept of biomimetic. And when we use polymers to do that, or when we use polymers or polymer based devices to do that, we call them as biomimetic devices or biomimetic polymers. So the typical concept is that you need to make things in such a way that they mimic the natural natural organisms or their mechanisms. So again, there are multiple examples, such as you have the artificial sensors, artificial skin, so that they exhibit similar properties as that of the human skin. You have artificial nose, so that they can try to smell, or try to smell multiple flavors, or you can say the mm, smell as such. So this is about the biomimetic polymers. There is something also called as the bio-inspired polymers. That is something very different. Over there you actually try to inspire from the nature and then try to incorporate into your systems. So it's like, if you are fascinated with a typical structure of a plant, then you try to reconstruct the similar structure in your device or basically the material, and then try to evaluate its properties. That kind of materials or the polymers that you develop are called as bio-inspired materials. So you inspire from the nature and try to incorporate that into your system. Biomimetic polymers or biomimetic systems are those wherein you develop your systems in such a way that they kind of mimic or resemble to proper or resemble or function something similar to what is available in the nature. So typical examples, or you can say that the examples that is discussed in the course is the synovial fluids. So that is more related to the biological system. So biological system, as you know, it's very complex. So the synovial fluids, it basically acts as an aqueous lubricating fluid in our human body. So they consist of the base layer, anchor layer and hydrated loose layers. So here what we need to actually do is to basically understand this understand their properties, understand how they act as a lubricant, and see or try to understand more in deep about this base, anchored and the hydrated loose layer, and then develop materials that can mimic the functions of what is happening in the human body. So that is more about the biomimetic systems. Finally, so this is all a gist. So again, you need to actually go through the lectures to have a deeper understanding of the concepts. Next, we move on towards the diffusion in the polymers. So polymeric diffusion. So diffusion as such, it means that there is a migration of a material from one region to the other region. So here we discussed about the diffusion of molecules, basically the mass. So this typically happens because of a particular gradient. So when there is a migration, so there should be some sort of a driving force behind that. So in case of diffusion, so in case of the diffusion in the solids or the liquids, the basic driving force is the concentration gradient, or to basically put it more in terms of a chemical engineering aspect, we can say that it is more of the gradient in the chemical potential. So due to the chemical potential gradient, there is a migration of the molecules from one region to the other region, or from the high or from high to low regions of chemical potential. So this diffusion is usually governed by certain law called as a Fick's law. So over there we try to relate the mass flux in terms of the concentration gradient and the diffusivity. So let me just write that also. So J, which is nothing but mass flux, is minus D. D is nothing but it's your diffusivity times dou C by dou X. So this is your gradient, the concentration gradient, the change in the concentration. So the negative sign typically represents because the movement is from high concentration region to the low concentration region. So higher the concentration gradient, higher is going to be a mass flux. So this diffusion, the diffusion of the molecules typically vary depending upon whether the diffusing medium is a gas, liquid or a solid. Again, this difference is, we can understand it easily, because in case of the gas, the molecules are easily able to move. So that is the reason it is more easier for the molecules to diffuse in the gas compared to the liquid, compared to that of the solids, because in solids the atoms are arranged in an orderly fashion. They are very close to each other, so the movement is very much restricted, the atomic movement is very much restricted. So that is the reason the diffusion is very difficult or is very slow in case of solids. How the diffusion happens in case of liquids and solids are very different. So in case of solids, the diffusion of the molecules happens through the hopping of the crystal lattice. Again, the way that happens can be very different. It could be basically because of the vacancies that are available in case of a solid, or the interstitial sites in the solid, or the crowding ion mechanism, or basically through the ground grain boundary. So these motions are going to be typically very random in case of the solids. If you see in case of polymers, polymers typically exhibit both the characteristic or the diffusion characteristic of solid as well as that of the liquid. So this here again the Tg will play an important role. So in case of the rubbery state or at temperatures higher than Tg, since the segmental mobility is going to be greater in these regions, the diffusion of the small molecules in the polymers is very similar to that of the diffusion in the liquids. However, if you see in case of the glassy state, that is going to be different, because in glassy state the segmental mobility is going to be very low. So the diffusion of the small molecules in case of the glassy state is going to be different. Again, that depends whether it is more, whether the glassy state is more of an amorphous polymer or amorphous state, or whether it has a crystalline lattice. If it is a crystalline lattice, then the space available for the molecular diffusion or for the diffusion of the small molecules is going to be limited. However, if in case of the amorphous polymer, then the small molecules do have the space for the diffusion. So the rate of diffusion in case of the glassy state is going will vary depending upon whether the polymers have more of a crystalline domain or that of an amorphous domain. Again, the diffusion in case of the polymers typically depends upon the percentage of free volume before and after Tg. So that's how the polymer diffusion is typically represented. So let me just first write this before I talk further in detail. Oh, sorry. So the diffusion of the small molecules in case of the polymers is given somewhat by something like this. So dmp equals dmp naught exponent minus ea by rt. So this is how you describe the diffusion of the small molecules in the polymer. So this the small molecules is typically is here represented in terms of m, and polymers is represented by p. So the Wm and Wp represents for the weight fraction. The V represents for Vp and Vm represents for the critical volume available for the jump. Psi represents for the ratio of the molar volumes of the polymer and the small molecules that you are taking under consideration. The VFV here it represents for the free volume that is available for the polymer, and the gamma represents for the overlap factor. So this is how you can actually write, or the mathematical equation that you can write for the diffusion of small molecules in the polymers. So again, as I keep saying that this is only a very brief overview, or you can say a gist of what was actually discussed in the course. So it's my request for everyone to go through the lectures so that you can have a better understanding of the concepts. Our discussion ends here. After this, we will start to solve few numerical problems related to what we have discussed in the previous class, as well as what we see in today's class. So if before proceeding to that, in case if you have any doubts to ask, feel free to ask any doubts if you have. So today's discussion is more of you can say it's more concept oriented or theoretical. We do not have much problems to solve based on what we have discussed today. So if you have any doubts related to what we have discussed so far, then you are welcome to ask. So we will start solving the numerical problems at starting from 6:20. We will begin with solving our numerical problems. So if you have any doubts, please feel free to ask me now. So if you do not have any doubts, then I think we can move forward. So the first question for today's session, it says that a copper wire upon unloading. So this question we should have solved it in the last session itself, but then due to time constraint we were unable to solve. So I have taken up with this question today. So the question reads somewhat like this: a copper wire upon loading. So you are going to load a copper wire. Its length is going to instantaneously increase to a length L, and then continues to elongate gradually. Upon unloading, the wire retracts to its length L. So original length is L. Then once you apply the load, it's going to elongate gradually. And once you unload it, the wire actually retracts back. According to the Maxwell model, which one of the following options given correlate the total strain, applied stress, modulus, material resistance to flow, that is viscosity eta, and then the elapsed time between loading and unloading. So how do you proceed to solve this? If in case if anyone has solved this from the last live interaction session, then you are welcome to share your answer. In case if not, then please take this time to solve this. So the Maxwell's model is something this one. So based on this, we need to solve. So let's me copy this. Anyone? Any idea on how to solve this question? Anyone with any answer or so if you just apply it in this equation, let's check. So stress will be S plus this is nothing but eta by G. So if we represent it this way, then if we express S E, then we will get S T by eta plus plus S by G. So this you can represent it E equals to S by G plus S by eta times T. So based on this, option C is correct. Is it right or is there any confusion? It's simple. You just take the Maxwell's equation and then you substitute the value, you substitute the variables what is given in the question into this equation and then just rearrange. Then here if you see, you can express E in terms of S, G, eta and T. Is there any doubt related to solving this question? This was quite a simple one, except for the fact that we need to know the Maxwell's equation, the fundamental equations of both the Weigett model and the Maxwell model. If we know, solving these questions will be relatively very easy. If you have any doubts, you are welcome to ask me if, in case if you have any questions. And the reason why we did not give dou sigma by dou t, or it's like the differential change in the stress, is because the applied stress here is a constant stress. So let's move on towards next question. The question is, it's a true or false question. So we are asked that which one of the following options is or are true for glass transition temperature or about glass transition temperature Tg. So the options is about Tg, the glass transforms from an amorphous solid to a viscous liquid. At Tg, glass transforms from an amorphous solid to a crystalline solid. Tg is dependent on the heat rate. Below Tg, nucleation and growth take place in glass. So which of the following option is true? Anyone? Which one is true? So B option is definitely wrong, because at Tg, glass transforms from an amorphous solid to crystalline solid. That's not going to happen, because in order for that to happen, it should go below Tg. So this is false. We'll represent this with red. Now, in the other three options, which one is true and which one is false? Anyone? Yes. So option A is the correct one. Above Tg, the amorphous solid gets converted to a viscous liquid. So this is what basically the definition of Tg as such. Tg is Tg is basically the temperature where the polymer goes from its glassy state to rubbery state, or it starts having a, or it basically starts to show the ability to flow. So that means it basically moves from an amorphous solid to a viscous liquid. So the other two, Tg is dependent on the heating rate. Below Tg, nucleation and growth takes place. What do you think about these two options? So does it mean that Tg is independent of the heating rate? So think about these two options. Let's go to the next question. Match the following properties with their respective units. We have four: notched izod impact strength, flexural strength, dielectric strength, and complex viscosity. So we are supposed to match. So what will be the right answer for this one? Or what should be the match? But before that, can anyone define what is the meaning of notched impact, izod impact strength, flexural strength, dielectric strength, and viscosity? So impact strength is nothing but it is basically the amount of energy that the material can absorb when a fixed load is suddenly applied to it. So this is typically determined by dividing impact energy by the thickness of the specimen. So energy, impact energy is usually measured in terms of joules. Joules by thickness gives joules per meter. So flexural strength is nothing but it is basically the strength to resist the deformation or kind of a bending under the loading condition. So that has a units of pascal. So here it is mentioned as megapascal. So Q show goes with 3. What is the definition of dielectric strength? How many of you know the exact definition of dielectric strength or idea on dielectric strength? This term is something specific when we discussed about electrochemical capacitors. So dielectric strength is nothing but it is basically the maximum amount of voltage that your material can withstand without breaking. So again, voltage, when we say, it has dielectric strength as such, it's a voltage. So that means R will be 4. So complex viscosity, as everyone know, it has a units of Pascal per Pascal second. So it is important to know the SI units for different physical parameters. But what is more important than that is to know the definition for variety of different terms that we usually encounter in this course. Moving towards our next question. If you have any doubts, please let me know. The definition for all these properties will be given separately when I upload the presentation. So moving towards our next question, let's do the true or false before we the match the following. So the true or false is, there are two questions here that you need to answer whether they are true or false. So the first question is, DSC can also be used to determine the crystallinity of the polymer. Is it true or is it false? This we discussed in the last live interaction session also. So one of the ways to determine a crystallinity in case of a polymer or any other material is using the X-ray diffraction. Depending upon the type of the diffraction pattern that we obtain, we can claim the or we can comment about the crystallinity of the sample, what type of crystallinity, what type of crystalline nature it is, and we can also comment about the percentage crystallinity present in that kind of material. But here the question is whether differential scanning calorimetry can also be used to determine the crystallinity of the sample. Is it true or is it false? If, then justify, of course. It is true because depending upon the melting as well as that of the crystalline peaks that we observe in case of the differential scanning calorimetry, we can comment about the crystallinity percentage of the sample. So if you remember, we discussed about the melting peak that we observe as well as the crystalline peak. So by knowing the enthalpy, the heat change, or by calculating the area under the curve, we can calculate the crystallinity in the samples. And then the next one is, so this one is true. Measurement of strain with time when constant stress is applied is called stress relaxation test. True or false? So here you are going to measure strain with respect to time, and you are going to keep the stress that you are applying as a constant stress. So that particular measure, this particular measurement is called stress relaxation test, whether it is true or false. This is basic definition. So, the measurement of strain with time when constant stress is applied is called stress relaxation test. This is false, right? Because for stress relaxation test, it is measurement of stress with time when constant strain is applied. But here we have the definition goes as such as that the strain is going to be measured with time, keeping the stress constant. So that will be the definition of creep test. Is that okay? I hope everyone will be knowing the definition. So this is false, right? I hope the things are clear with respect to true or false. So now let's move on to the question before this one, which is the match the following. So the question goes on like this: match the material classification in the column A to column B. So in column A you have different types of blends and composites which you are supposed to match it with their respective material, or you can say that you have materials in column B which you have to match with their respective classification in column A. So you have miscible blend, immiscible blend, compatibilized blend, and polymer composites. So what could be the classification, or what could be the, or what polymers will come under each classification? So blend, I hope everybody will be knowing. It is nothing but when two polymers are mixed together, what you obtain is a polymer blend. Now based on that, again as we discussed in the few minutes before, there are multiple types of blends: miscible, immiscible and compatibilized blend. So what could be there? Any guesses on which one can be matched with what classification, or what type of blend, what any particular system can be? Any idea? Anyone? So let us do one thing. Let us keep thinking about this question, and I think let, we can take this in the next live interaction session, so that we will be, you guys can also have a thought on this, which particular polymer will come under what particular blend classification, and then let's look at this in the next live interaction session. So in case if you have any doubts so far, please feel free to ask before we progress for the next question. Now let's solve some simple problems for today's session. Let's start with this question. A nylon sample which has a cross sectional area of 0.03 meter square is subjected to a creep load of 10 kilonewton. The load is removed after a duration of 60 seconds. Young's modulus and the viscosity for the nylon is given as 1 gigapascal and 300 gigapoise. Calculate the compliance of the sample. So how to calculate the compliance of the sample? So compliance, if you remember, it's something that we discussed in last class, which is usually represented by D. So, this we discussed in the last session. I'm just going to give you the formula here. So here if you see, the stress is constant 10 kilonewtons, so the strain is going to vary. So that is the reason why it is called as a, why it is called as creep. So compliance, as we discussed last time, it is basically defined as the strain as a function of time by constant stress that is applied. So now you just need to plug in the numbers here and calculate the value of the compliance. So let calculate and let me know. Lambda is the relaxation time. T here is 60 seconds. So now we are supposed to calculate the value of lambda, which is the relaxation time. So has anyone calculated the value of lambda relaxation time? So relaxation time can be defined as, relaxation time is nothing but it is the ratio of the viscosity to the Young's modulus. So viscosity here it is given in terms of gigapoise. So we need to convert gigapoise to poise, and then from poise we need to convert that into Pascal second. So 300 gigapoise is nothing but, well, let us write it this way. Okay, 300 gigapoise is nothing but 300 times 10 to the power 9 times. So this is poise, these many poise. Now from poise to Pascal per second, we need to multiply that with 0.1. This entire divided by their Young's modulus. That value, you know, it is given in the question 10 power 9. So if we calculate this, then what we get is 30. Am I right? Yes. 30 is the value of lambda, or you can say lambda r also. So then substituting the value of lambda in this equation, so now the compliance at t equals to 60 seconds is going to be 1 by 10 to the power 9 1 minus exponential of minus 60 by 30 is minus 2. So then compliance at t equal to 60 second is going to be, so let me take the calculator once again. Point 1353. So 1 by 10 power 9 1353. So 1 minus 0.1353 is 0.8647. So compliance after 60 seconds is going to be 0. 10 to the power minus 9. Is the answer correct, or do you guys have any other different answer? Anyone with any other different answer? So what will be the units? Since compliance is 1 by elastic modulus, it is going to be 1 by Newton per meter square or meter square per Newton. So this is the value of the compliance of the sample after t equals to 60 seconds. And one more thing here is, since we are not knowing which model to use, so I have calculated the compliance using Kelvin Weigert model. But here you can also use Maxwell's model to calculate the compliance. So you can take that as a task to calculate the compliance value using the other models also. So let us discuss about what will be the answer, or what kind of contrasting difference, is there any contrasting difference in the answer in the next live interaction session. So I am giving it to you as a task to calculate the compliance of the sample using the other model also. Conclude the session for today. If you have any doubts, you are welcome to ask me right now, or else we can conclude the session. If you have any doubts, you are welcome to ask me. In case if you have no doubts, then I think I can conclude the session for today. So let me just stop sharing my screen. So thank you all for, let me conclude the session. So thank you all for joining today's live interaction session. Our next live interaction session will be on 21st September, same 5 p.m. to 7 p.m. I take this as an opportunity to thank Professor Abhijit Deshpande sir, as well as the NPTEL team, for providing me this opportunity to interact with you all on this Sunday afternoon. So till we meet for the next time, have a great week ahead. Thank you and bye.